Every second, the Sun converts approximately 600 million tons of hydrogen into helium through nuclear fusion, releasing energy equivalent to 90 billion megatons of TNT. This process occurs continuously, without mechanical pumps, magnetic confinement coils, laser systems, or any of the elaborate machinery that humanity requires to achieve even momentary fusion in laboratories. The Sun accomplishes what our most sophisticated technology struggles to sustain: sustained, controlled fusion, producing net energy gain using nothing but gravity, quantum mechanics, and the fundamental properties of matter under extreme conditions. The paradox confronting nuclear physicists for decades was straightforward. Fusion requires temperatures exceeding 10 million Kelvin to overcome the electromagnetic repulsion between positively charged atomic nuclei. Human fusion experiments achieve these temperatures in laboratory plasmas confined by powerful magnetic fields generated by enormous superconducting magnets. Yet the Sun's core, at approximately 15 million Kelvin, achieves sustained fusion through mechanisms that seem, at first glance, embarrassingly simple. Just compress hydrogen sufficiently through gravitational collapse, and fusion begins naturally. The reality proves far more subtle and elegant. The Sun doesn't overcome the electromagnetic barrier between protons through brute force alone. Instead, quantum mechanics provides an escape route. Quantum tunneling allows protons to pass through the energy barrier, separating them from the strong nuclear force's attractive region, enabling fusion at temperatures far below what classical physics would require. This quantum mechanical pathway, combined with the Sun's enormous mass providing gravitational confinement, creates conditions where fusion becomes inevitable. Understanding stellar fusion requires abandoning intuitions derived from human engineering. We build machines with discrete components: power supplies, confinement vessels, fuel injection systems, energy extraction mechanisms, all controlled through external intervention. Stars are self-regulating systems where gravity provides both the compression creating fusion conditions and the confinement preventing the star from flying apart. The energy released by fusion creates pressure that balances gravity, establishing equilibrium without external control systems. The temperature of 15 million Kelvin in the solar core isn't arbitrary. It emerges from the balance between gravitational compression and thermal pressure. If fusion rates increase, the core heats. Pressure rises, the core expands slightly, density decreases, and fusion rates decline back toward equilibrium. If fusion slows, the core cools, contracts under gravity, density increases, and fusion rates accelerate. This self-regulation, called hydrostatic equilibrium, maintains stable energy production over billions of years without external adjustment. The fusion process itself differs fundamentally from human-engineered reactions. Terrestrial fusion experiments typically use deuterium and tritium hydrogen isotopes with neutrons added to their nuclei because these fuse at lower temperatures than ordinary hydrogen. The Sun uses ordinary hydrogen, fusing protons directly through a multi-step process called the proton-proton chain. This process is extraordinarily slow. Individual protons in the solar core wait billions of years on average before fusing, yet the Sun contains so many protons that billions of fusion reactions occur every second. The energy produced in the core doesn't immediately escape to space. Photons created in fusion reactions scatter through the dense solar plasma, taking a random walk that requires 100,000 to 200,000 years to traverse from core to surface, despite the Sun's radius being t. Reversible by light in just 2.3 seconds through vacuum. This delayed energy transport acts as a buffer, smoothing short-term fusion rate fluctuations and contributing to the Sun's long-term stability. The machinery-free nature of stellar fusion emerges from physics operating at scales and conditions where mechanical engineering concepts break down. There are no solid components because temperatures vaporize all materials. There are no magnetic coils because the plasma's own magnetic fields, generated by convection and differential rotation, dominate externally applied fields. There are no fuel pumps because gravitational stratification naturally concentrates the lightest element, hydrogen, toward the core where it's needed. Human fusion research aims to replicate stellar conditions on Earth, facing the challenge that we cannot access gravity's enormous compressive power. A star's mass, the Sun, contains 333,000 times Earth's mass, creates gravitational fields that compress matter to densities 150 times that of liquid water at the core. Recreating these conditions without gravity requires either magnetic fields confining low density plasma heated to hundreds of millions of Kelvin, or powerful lasers compressing fuel pellets to extreme densities for brief moments. Tonight we're going to explore exactly how stars achieve sustained fusion without technology, examining the role of gravity in creating and maintaining fusion conditions. How quantum tunneling enables reactions at temperatures lower than classical physics predicts. Why the fusion process naturally regulates itself. How energy travels from stellar cores to surfaces. And what happens in stars of different masses where fusion operates under varying conditions. Before we begin exploring stellar structure and nuclear physics, if you're fascinated by how nature accomplishes through fundamental physics what humanity struggles to achieve through engineering, subscribe and hit the thumbs up button. And here's a question: if we could harness gravity the way stars do, would that solve Earth's energy problems, or would it create new challenges? Comment below, I'll pin the most thoughtful answer. The Sun has been fusing hydrogen into helium for 4.6 billion years and will continue for approximately 5 billion more, all without maintenance, refueling, or external control. Understanding this natural fusion reactor reveals principles that might inform human fusion efforts while demonstrating the elegance of physics operating at cosmic scales. Stars don't need machines because they are machines self-assembling, self-regulating fusion reactors built from nothing but gravity and quantum mechanics. Now let's begin by understanding exactly what fusion is, why it's difficult to achieve, and what conditions are necessary for atomic nuclei to overcome their mutual repulsion and merge. Chapter 1: The Fusion Challenge. Nuclear fusion. The process of combining light atomic nuclei into heavier ones releases enormous energy because the product nucleus has slightly less mass than the sum of its components. This mass deficit, typically 0.1 to 1% of the initial mass, converts to energy according to Einstein's equation E equals mc, where the speed of light squared provides a huge conversion factor. 1 kilogram of matter converted entirely to energy yields approximately 90 trillion joules, equivalent to the explosion of 21 megatons of TNT. The fundamental challenge preventing fusion stems from electromagnetic repulsion between atomic nuclei. Nuclei contain protons, each carrying positive electric charge. Like charges repel through the electromagnetic force following Coulomb's law, F equals kq r squared, where k is Coulomb's constant, q and q are the charges, and r is the separation distance. For two protons approaching each other, this repulsive force increases dramatically as distance decreases. The energy barrier created by electromagnetic repulsion is called the Coulomb barrier. Two protons approaching from rest must possess sufficient kinetic energy to overcome this barrier and reach distances where the strong nuclear force, the force binding protons and neutrons into nuclei, becomes dominant. The strong force operates only at extremely short ranges, approximately 10 meters 1 femtometer, but at these distances it vastly exceeds electromagnetic repulsion. Calculating the Coulomb barrier height for two protons yields approximately 0.5 MeV megaelectron volts. Converting to temperature through the relationship between average thermal energy and temperature equals 3/2 kT, where K is Boltzmann's constant, gives a temperature of approximately 4 billion Kelvin required for protons to overcome the barrier through thermal energy alone. This temperature far exceeds the 15 million Kelvin in the Sun's core. Creating an apparent paradox, the Sun is too cold for fusion based on classical physics. The resolution involves quantum mechanics. Heisenberg's uncertainty principle permits particles to temporarily borrow energy, and quantum wave functions allow particles to exist with non-zero probability in classically forbidden regions. A proton approaching the Coulomb barrier has some probability of appearing on the other side through quantum tunneling, passing through rather than climbing over the energy barrier. This probability is exponentially small but non-zero, enabling fusion at temperatures far below the classical requirement. The tunneling probability depends exponentially on particle energy and barrier width. Higher energy protons tunnel more easily, while heavier nuclei with larger charges create taller, wider barriers that suppress tunneling. This explains why hydrogen fusion occurs most readily. Single protons create the smallest Coulomb barrier. Helium nuclei with 2 protons each create barriers roughly 4 times higher, requiring temperatures exceeding 100 million Kelvin for significant fusion rates. The fusion cross-section, a measure of reaction probability, quantifies how likely colliding nuclei are to fuse. For proton-proton fusion at solar core temperatures, the cross-section is approximately 10 square centimeters, vanishingly small. This means individual protons can collide billions of times without fusing. The average proton in the solar core waits approximately 9 billion years before undergoing fusion, a timescale comparable to the age of the universe. Despite this extraordinarily low fusion probability per collision, the Sun sustains enormous fusion rates through sheer numbers. The solar core contains roughly 10 protons, and at 15 million Kelvin these protons move at average speeds of approximately 500 kilometers per second, producing countless collisions every second. Even with fusion probability of 1 in 10 collisions, the total fusion rate reaches approximately 10 reactions per second, sufficient to power the Sun's luminosity. The energy release per fusion reaction in the Sun's proton-proton chain totals approximately 26.7 MeV, produced through multiple steps converting 4 protons into 1 helium for nucleus, 2 positrons, and 2 neutrinos. The 26.7 MeV appears as kinetic energy of products and gamma-ray photons, which thermalize through collisions with surrounding plasma. This energy must balance the Sun's luminosity, the total energy radiated from its surface per second. The power output calculation confirms internal consistency. The Sun's luminosity is approximately 3.8 times 10 watts. Dividing by the energy per fusion, 26.7 MeV approximately equals 4.3 times 10 joules, gives roughly 9-10 fusion reactions per second required to sustain solar output. This matches the estimate from fusion cross-sections and core particle density, confirming our understanding of stellar fusion physics. Terrestrial fusion experiments face different constraints. We cannot access stellar masses producing gravitational confinement, so we must heat plasma to hundreds of millions of Kelvin far hotter than stellar cores to compensate for lower densities. We use magnetic confinement tokamaks, stellarators, or inertial confinement laser fusion to contain the hot plasma temporarily. The challenge is sustaining these extreme conditions long enough for fusion reactions to produce more energy than the confinement systems consume. The National Ignition Facility achieved a milestone in December 2020 by producing fusion reactions yielding more energy than the laser energy delivered to the fuel capsule, a condition called ignition. However, the laser energy represented only a few % of total electrical input to the laser system, meaning overall energy gain including inefficiencies remained negative. Practical fusion power requires sustaining this condition with high repetition rate and efficient energy conversion, challenges remaining unsolved. Magnetic confinement fusion, pursued through projects like ITER, International Thermonuclear Experimental Reactor under construction in France, aims to confine deuterium-tritium plasma at 150 million Kelvin in a tokamak magnetic configuration. ITER is designed to produce 500 megawatts of fusion power from 50 megawatts of heating power, achieving Q equals 10 energy gain factor. However, ITER won't generate electricity. It's a physics experiment demonstrating sustained high-gain fusion. Practical power plants would require additional development. The fundamental difference between stellar and terrestrial fusion lies in the energy source for confinement and heating. Stars use gravitational potential energy, matter falling into the gravitational well heats through compression, reaching fusion temperatures naturally. Once fusion begins, the energy release maintains thermal pressure balance and gravity. This creates self-sustaining equilibrium requiring no external energy input. Terrestrial fusion requires external energy to create and maintain fusion conditions. Magnetic fields must be powered by external electrical supplies. Lasers must be driven by electricity from conventional sources. Until fusion produces more energy than these systems consume, including all inefficiencies in energy conversion and confinement, fusion cannot serve as net energy source. Stars face no such constraint because gravitational confinement requires no energy input. Gravity is free. The Lawson criterion quantifies the conditions necessary for practical fusion energy gain, the product of plasma density, confinement time, and temperature must exceed a threshold value. For deuterium-tritium fusion, this requires N times tau times T is greater than or equal to 3 times 10 squared eV/second per cubic meter, where N is density, tau is confinement time, and T is temperature. Meeting this criterion through magnetic or inertial confinement represents the central challenge of fusion energy research. Stars easily satisfy Lawson-like criteria because their confinement time is effectively infinite. Stars remain stable for billions of years and their densities, while lower than fusion pellets in inertial confinement, are sustained indefinitely. The combination of modest temperature by fusion standards, high density, and unlimited confinement time creates conditions where even slow fusion reactions accumulate to enormous total energy output over stellar lifetimes. The fusion gain factor Q ratio of fusion power output to heating power input must substantially exceed unity for practical energy production. Experimental fusion devices have achieved Q approaching 1 in best cases, with theoretical break-even Q equals 1 now demonstrated. Commercial fusion power plants would require Q approximately equals 20 to 30 to account for conversion inefficiencies and operating costs. Stars operate at effectively infinite Q because they require no external heating power. Fusion itself provides the thermal pressure maintaining core temperature. Understanding the fusion challenge reveals why stars accomplish naturally what human technology struggles to replicate. Gravity provides the essential ingredient: sustained, stable confinement at high density that laboratory fusion seeks to recreate through electromagnetic forces. Stars don't overcome the fusion challenge through superior technology but through physics operating at planetary mass scales where gravity dominates all other forces. Chapter 2: Stellar Structure. Stars are not uniform spheres of gas but stratified structures with distinct layers characterized by different physical processes, temperatures, densities, and mechanisms of energy transport. Understanding stellar structure reveals how gravitational compression creates fusion conditions in cores while maintaining stability through layers extending from unimaginably hot and dense centers to relatively cool surfaces. The Sun's core, the innermost region extending to approximately 0.25 solar radii, roughly 175,000 kilometers from center, contains the conditions necessary for fusion. Temperature reaches approximately 15 million Kelvin. Density exceeds 150,000 kilograms per cubic meter, 150 times water's density. And pressure surpasses 250 billion atmospheres. These extreme conditions result from gravitational compression as the overlying solar mass, roughly to 10 kilograms, presses downward. The core's composition has evolved over the Sun's 4.6 billion year lifetime. Initially approximately 71% hydrogen and 27% helium by mass, fusion has converted roughly half the core hydrogen into helium, giving current composition of approximately 34% hydrogen and 64% helium. This compositional evolution affects stellar evolution. Increasing helium abundance raises mean molecular weight, requiring higher core temperature to maintain pressure support against gravity. The radiative zone extends from approximately 0.25 to 0.7 solar radii, encompassing the region where energy transport occurs primarily through photon diffusion. Temperatures range from approximately 7 million Kelvin at the base to 2 million Kelvin at the top. Density decreases from roughly 20,000 kilograms m to 200 kilograms per cubic meter. In this zone, photons created in the core scatter countless times off free electrons and ions, slowly diffusing outward in a random walk. The photon diffusion timescale, how long photons take to traverse the radiative zone, is extraordinarily long despite relatively short travel distances. Each photon travels approximately 1 centimeter on average before scattering, meaning a photon must take roughly 10 steps to cover the radiative zone's 300,000 kilometer extent. The total transit time reaches 100,000 to 200,000 years, meaning sunlight reaching Earth today originated from fusion reactions that occurred before modern humans evolved. The convection zone extends from approximately 0.7 solar radii to the visible surface. Here, energy transport transitions from radiation to convection, bulk motion of plasma transporting heat more efficiently than photon diffusion. Hot plasma rises from the base of the convection zone, cools as it approaches the surface, and sinks back down to be reheated. This creates turbulent convective cells visible as granulation on the solar surface. The temperature gradient. How rapidly temperature changes with radius determines whether convection occurs. If the gradient becomes too steep for radiative diffusion to transport energy efficiently, the plasma becomes unstable to convection. The Schwarzschild criterion for convective instability compares the actual temperature gradient with the adiabatic gradient, the temperature change for plasma rising without exchanging heat with surroundings. When actual gradient exceeds adiabatic, convection begins. The photosphere, the visible surface of the sun, represents the layer from which photons can finally escape to space after their long journey from the core. Temperature drops to approximately 5,800 Kelvin, defining the sun's effective temperature and determining its spectral energy distribution. The photosphere's depth is just a few hundred kilometers, extraordinarily thin compared to the sun's 700,000 kilometer radius, making it effectively a surface despite being gaseous. Above the photosphere lie the chromosphere and corona, the sun's outer atmosphere, heated by mechanisms not yet fully understood. The chromosphere, extending roughly 2,000 to 3,000 kilometers above the photosphere, shows temperature rising from 6,000 to 20,000 Kelvin. The corona extends millions of kilometers with temperatures exceeding 1 million Kelvin. This temperature inversion, increasing temperature with distance from the heat source, violates naive expectations and requires energy input from magnetic fields or wave dissipation. Hydrostatic equilibrium, the balance between gravitational compression and thermal pressure, governs stellar structure. At each radius within the star, the inward gravitational force per unit volume must equal the outward pressure gradient. dP doctor equals rho or gmr r squared, where P is pressure, r is radius, rho is density, g is gravitational constant, and mr is the mass contained within radius r. This differential equation, combined with equations for energy generation and transport, determines stellar structure. The equation of state relating pressure to density and temperature for the solar interior well approximated by ideal gas law. P equals nkt, where n is number density and k is Boltzmann's constant, completes the set of equations describing stellar structure. In reality, the equation of state is more complex, accounting for radiation pressure, degeneracy pressure in dense regions, and departures from ideal gas behavior. But ideal gas provides good first approximation for main sequence stars. Energy generation rate, how much fusion energy is produced per unit mass per unit time, depends strongly on temperature. For the proton-proton chain dominating solar energy production, the rate approximately follows epsilon, varies as rho t, where epsilon is energy generation rate per unit mass, rho is density, and t is temperature. This strong temperature dependence creates a natural thermostat. If core temperature increases slightly, fusion rate spikes, producing extra energy that expands and cools the core until equilibrium restores. Opacity, the plasma's effectiveness at absorbing and scattering photons, determines how easily energy escapes. Through radiative diffusion, opacity depends on temperature, density, and composition, with contributions from free electrons scattering photons, Thomson scattering, bound electrons absorbing photons, bound free and bound transitions, and free electrons accelerating in ion electric fields and emitting or absorbing photons. Free processes. Higher opacity means photons travel shorter distances between interactions, slowing energy transport. The Rosseland mean opacity, a specific average of opacity weighted by temperature gradient and energy flux, appears in the radiative diffusion equation relating energy flux to temperature gradient. F equals for a C3 cubed dt dr kappa, where F is energy flux, A is radiation constant, C is light speed, and kappa is Rosseland mean opacity. This equation determines the temperature gradient required to transport energy at rate matching core fusion production. Stellar evolution occurs as fusion converts hydrogen to helium, changing core composition and structure. The increasing helium fraction raises mean molecular weight, requiring higher temperature to maintain pressure at given density. Core temperature slowly rises, accelerating fusion rates and increasing luminosity. The sun has brightened by approximately 30% since formation and will continue brightening as core evolution progresses. The main sequence, the band in the Hertzsprung-Russell diagram where stars spend most of their lives, represents stars in hydrostatic equilibrium burning hydrogen in their cores. More massive stars have higher core temperatures and densities, producing higher luminosities and shorter lifetimes. The mass-luminosity relation, approximately L, varies as m cubed. For solar mass stars, means a star twice the Sun's mass has roughly 11 times solar luminosity, exhausting fuel far faster than its mass advantage suggests. Different stellar masses exhibit different internal structures. Low-mass stars below approximately 0.35 solar masses are fully convective. Energy transport occurs through convection throughout the star, mixing material from core to surface. Intermediate mass stars like the Sun have radiative cores and convective envelopes. High-mass stars above approximately 1.3 solar masses have convective cores and radiative envelopes. With carbon-nitrogen-oxygen CNO cycle fusion concentrated near the center driving convection. Stellar structure models, computed by solving the coupled differential equations of hydrostatic equilibrium, energy generation, energy transport, and mass conservation, accurately predict observed stellar properties. Agreement between theoretical models and observations. Stellar luminosities, RD, effective temperatures. Spectroscopic abundances confirms our understanding of stellar physics and fusion processes. Powering stars. The self-assembling nature of stellar structure emerges from these equations. A collapsing gas cloud heats through gravitational compression until core temperature reaches fusion threshold. Fusion begins, releasing energy that creates thermal pressure. Pressure balances gravity, halting collapse. The star settles into equilibrium configuration determined by mass and composition, maintaining stability for billions of years. No external assembly or control required, just gravity and quantum mechanics operating under laws of physics. Chapter 3: Gravitational compression. Gravity, the fundamental force attracting masses toward each other, provides the essential mechanism creating fusion conditions in stellar cores. Understanding how gravitational compression produces the extreme temperatures and densities necessary for fusion reveals why massive objects naturally become fusion reactors while smaller objects cannot achieve sustained fusion regardless of composition. Newton's law of universal gravitation, F equals gm or squared, quantifies the attractive force between masses m and mm separated by distance r, where g is the gravitational constant, approximately 6.67 for times 10 t in a square meter per kilogram squared, for a self-gravitating sphere like a star. The gravitational force at any radius comes from the mass interior to that radius, with exterior mass contributing zero net force by the shell theorem. The gravitational potential energy of an object at distance r from a mass m is U equals gmmr, where negative sign indicates bound system energy must be added to separate the objects to infinite distance. For a star, the total gravitational potential energy involves integrating contributions from all mass elements at all radii. For a uniform density sphere, the result is U approximately equals minus 3,000,005 r, where m is total mass and r is radius. When a gas cloud collapses under its own gravity, gravitational potential energy converts to kinetic energy of infall and thermal energy as the gas compresses. The virial theorem for self-gravitating systems in equilibrium relates thermal energy underscore thermal to gravitational potential energy underscore thermal equals U2. This means that in achieving equilibrium, roughly half the gravitational energy released goes into thermal energy while half is radiated away. The temperature resulting from gravitational compression can be estimated from the virial theorem. For a cloud of hydrogen with total mass m and radius r, the thermal energy is approximately underscore thermal equals 3/2 n kT, where n is the number of particles and k is Boltzmann's constant. Setting this equal to U2 equals 3,000,000 n r and solving for temperature gives T approximately equals gmm underscore p of 5 Ker, where m underscore p is proton mass. Applying this to the Sun, m equals to times 10 kilograms, r equals 710 meters yields core temperature of order 10 million Kelvin, remarkably close to the actual value of approximately 15 million Kelvin. This confirms that gravitational compression alone, without fusion, can produce temperatures approaching those necessary for fusion. Indeed, Pre-main sequence stars shine through gravitational contraction before fusion ignites. The minimum mass for sustained hydrogen fusion. The hydrogen burning minimum mass is approximately 0.08 solar masses, or roughly 80 Jupiter masses. Objects below this mass never achieve core temperatures and densities sufficient for sustained proton-proton chain fusion. These failed stars, called brown dwarfs, undergo brief deuterium fusion, which occurs at lower temperatures but eventually cool as they slowly radiate away their gravitational contraction energy. The mass-temperature relationship explains why more massive stars have hotter cores. Higher mass produces stronger gravitational compression, requiring higher internal pressure for hydrostatic equilibrium. Higher pressure at given density requires higher temperature through the ideal gas law P equals nKT. Thus, stellar mass directly determines core temperature, with massive stars achieving temperatures exceeding 30 million Kelvin while low-mass red dwarfs barely exceed fusion threshold. The density achieved through gravitational compression depends on both mass and composition. Pure hydrogen gas collapses to higher central densities than gas with heavier elements because hydrogen's lower mean molecular weight allows more particles per unit mass. Increasing pressure for given temperature and density, the solar core's density of approximately 150,000 kilograms m represents balance between gravitational compression and thermal pressure at the achieved temperature. Electron degeneracy pressure. Quantum mechanical pressurizing from Pauli exclusion principle forbidding multiple fermions occupying identical quantum states becomes important. In very dense matter, in the solar core, degeneracy pressure contributes but doesn't dominate. Thermal pressure provides most support against gravity and white dwarfs, where fusion has ceased and contraction continues until degeneracy dominates. Electron degeneracy pressure alone supports the star against gravitational collapse. The Lane-Emden equation describes the structure of self-gravitating polytropic spheres. Objects where pressure relates to density through P varies as rho gamma, where gamma is the polytropic index. For fully ionized ideal gas, gamma equals 5/3. Solving the Lane-Emden equation with appropriate boundary conditions yields density and pressure profiles as functions of radius. Describing how gravitational compression creates centrally concentrated structure. The gravitational binding energy, the energy required to completely disperse a star's mass to infinity for the Sun, is approximately 10 joules. This represents the energy released during the Sun's formation from a diffuse molecular cloud. For comparison, the Sun's total nuclear energy budget, the energy available from converting all core hydrogen to helium, is roughly 10 joules, about 1/400th of the binding energy. This explains why stars shine primarily through fusion rather than gravitational contraction. Pre-main sequence evolution traces a star's path from initial collapse to fusion ignition. The Hayashi track represents early contraction where the star is fully convective and relatively cool. As contraction continues and core temperature rises, the star transitions to the Henny track where the core becomes radiative. Eventually, core temperature reaches approximately 3 million Kelvin. Deuterium fusion begins, providing brief energy source. Further contraction raises temperature to approximately 10 million Kelvin, and sustained hydrogen fusion ignites. The Kelvin-Helmholtz timescale estimates how long the star can shine through gravitational contraction without fusion. T_K approximately equals gm/L, where R is radius and L is luminosity. For the Sun, this yields approximately 30 million years. Geological evidence proving Earth is billions of years old, far exceeding the Kelvin-Helmholtz timescale, required physicists to seek energy source east beyond gravitational contraction, leading to discovery that nuclear fusion powers stars, Jupiter, with mass approximately 0.01 solar masses. Illustrates gravitational compression's limits. Jupiter's core temperature reaches approximately 20,000 to 30,000 Kelvin hot, but for below fusion threshold. No amount of additional mass from hydrogen or helium alone would ignite fusion. Jupiter would need roughly 80 times more mass to achieve the conditions necessary for sustained hydrogen burning. Gravitational contraction continues even after fusion ignites, though at much slower rates. As fusion converts hydrogen to helium, mean molecular weight increases, requiring higher temperature to maintain pressure. The core slowly contracts, Temperature rises, fusion rate accelerates, and luminosity increases. This gradual evolution causes the Sun to brighten approximately 1% per 100 million years, a rate imperceptible on human timescales but significant over billions of years. The uniformity of gravitational compression operating equally in all directions and throughout the star's volume creates spherical symmetry. Stars are spheres because gravity pulls equally toward the center from all directions, and hydrostatic equilibrium establishes spherically symmetric pressure distribution. Rotation can distort this symmetry slightly, creating oblate shapes. But gravity's dominance maintains near-spherical form, the energy source for achieving fusion. Conditions thus requires no machinery, no external power, no control systems, just mass. Gather sufficient hydrogen in one place, and gravity automatically compresses it to fusion-igniting conditions. The process is deterministic, requiring no assembly or intervention. This represents the fundamental difference between stars and human-engineered fusion. Stars use gravity's free, ubiquitous compression, while we must artificially create and maintain extreme conditions using energy-intensive electromagnetic confinement. The impossibility of replicating gravitational confinement on Earth follows from the scaling of gravitational force with mass. Even assembling thousands of tons of hydrogen, the largest mass humans can manipulate, produces negligible gravitational compression. Jupiter demonstrates that even planetary masses fall short. Stellar masses are required, and stellar masses naturally collapse into stars. Humanity cannot access gravitational fusion because we cannot gather stellar masses, and gathering stellar masses automatically creates stars.